Hi there, I'm Ran, and in this video I'd like to guide you through my poster here. This is a joint work with Professor Jim Dai from Cornell University and CU Education Gen, and Professor Kostis Mouglaras, Dean of Business School in Columbia University. The question we're targeting is the following. So consider a ride-hailing platform that is provided with some information about drivers' outside opportunities, namely their income goals. What is the value of that information, and how can the platform utilize it in order to maintain drivers' satisfaction and commitment towards the platform? Imagine the following process. There is a city modeled as the unit interval. Here we consider a segment between 0 and x, and n drivers are circulating that city. They divide it into two types, L and H, with different opportunity costs, kappa L, which is lower than kappa H. The proportion of each type is given by theta L and theta H. Drivers can be either busy or available, and there are passengers arriving following some stochastic process at random locations. Once a passenger arrives at a location S, they must be matched with a driver within the pickup region, here denoted by S plus minus some delta. And the policy determines which available drivers to pick. Once matched, a driver becomes busy for the duration of the ride and generates revenue at rate R. They then go back to available once they reach the passenger's destination. If no driver is available within the pickup region, the ride is lost. We represent the system state as a pair of functions, qi, I for each type, at point x and time t. That is the proportion of type I drivers that were both available and in locations between 0 and x. We will consider two policies. One is min rev, which assigns the ride to the available driver whose accumulated revenue by time t is minimal. The other is mean weight rev, which is exactly like mean rev, except that it considers the accumulated revenue divided by the opportunity cost. In equilibrium, each driver participates if and only if they can make revenue at a rate at least as high as their kappa. Here you can see simulation results for a market with 260 drivers, 50% of each type. In equilibrium under mean rev, the average revenue for a driver is slightly below kappa H, and so type H drivers do not wish to join. All the workforce for the platform consists of 130 drivers, all of them are type L. If we switch to mean weight rev, the equilibrium revenue rate for type H increases, and so all of them would join. The equilibrium revenue rate for type L decreases, but not below 0.8. So we double the workforce for the platform. Analyzing the discrete model is difficult, and so what we do, we analyze a mean-field fluid system that provides good approximation for the discrete one under the assumption that the market size is large. Our mean-field formulation relies on two observations. One is that when n is large, drivers' scaled locations form a spatial Poisson process. The other one is that when t is large, the long-run revenue rates of drivers exhibit a state space collapse phenomena. Empirical evidence for these two statements are shown in figures 3 and 4 for n equals 200. We also show that for a fixed time point t, as n goes to infinity, the state of the discrete system approaches the fluid solution. This is a desired behavior when dealing with fluid limits of stochastic processes. Using our mean-field model, we were able to prove analytically the results I described to you earlier. That is, mean weight rev is always better than mean rev in equilibrium. It can increase the total participation rate by a factor of up to 2, which in turn can lead to up to 100% improvement in system throughput. Thank you for listening. If you're interested in learning more about this project, please reach out.